This is lesson 2 of chapter 8, and we will be talking about covalent compounds. Last lesson we took a look at ionic compounds, here covalent compounds. Let's first take a look at some of the characteristics or properties of covalent compounds. They in general have low melting points and low boiling points, which means that most of them, or a lot of them, you'll find as liquids and gases at room temperature. And recall that none of the ionic compounds existed as liquids and gases, only solids. Covalent compounds also vaporize readily, and this is again due to the fact that they have, as you'll see, weak bonds between them. For the same reason why they'll melt low, and they do not conduct electricity when dissolved in water. Some of these compounds, or many of them, will sublimate. A good number of them, not many, but a good number of them. In this case, this is dry ice, if you recall, and dry ice, a favorite of many aspiring young chemists, is carbon dioxide, which essentially is a covalent compound. This one here, mothballs, also sublimates, and this is a carbon-hydrogen compound, which again tells you have two nonmetals, you got yourself a covalent compound, because recall nonmetals form covalent compounds. Let's take a look at the how this happens. So we have two hydrogen atoms here, and as they come together, what happens is their nuclei start to attract each other. And the reason they start to attract each other is because the electron cloud, the negative charge of the electron cloud of this atom gets attracted by the nucleus of this atom. And eventually what will happen is the electron clouds of both atoms, remember the valence electron clouds, get to be spread out over two of the nuclei. And that's how a covalent compound forms. So if you analyze it a little more closely, this electron cloud, essentially the electrons around the outside are attracted to both nuclei now. So there is an attraction between the nucleus and the electron. Notice there's a 1, 2, 3, 4 attractive forces here. There's a repulsion between the two nuclei. That's why the two nuclei, as you see here, will kind of spread out, and they'll try to minimize their, how close they come together. And then the electrons, obviously, the electrons from both atoms also repel one another, but they accommodate each other by actually reversing their spins so they can coexist. So essentially what happens is the electron clouds are fused together because they are attracted to the other atom's nucleus, positively charged nucleus. The covalent bonds could be what are called polar, and the electrons in this case, polarity means that the electrons are not equally shared. So in the case of, if you have two fluorine atoms, then two fluorine atoms will essentially share with the same intensity or the same strength. With hydrogen and fluoride, for example, if you have a hydrogen atom and a fluorine atom, the electron density around it gets pulled more toward the fluorine. And this is due to the fact that fluorine has a higher affinity for electrons. So fluorine pulls harder on the electrons it shares with hydrogen. And so the electron density will be mostly on the fluorine end and not on the hydrogen end. In fact, here we use red to show a higher electron density, a lot more electron density, and blue we show low electron density is the idea. And this concept is given to us by something called electronegativity. So electronegativity is another trend on the periodic table, and it is the ability of atoms in a molecule to attract electrons to themselves. So it's a measure of how much the atom desires electrons. This is close to electron affinity. Remember we talked about electron affinity in the in the previous chapter. Electron affinity is how much energy it gives off when it receives an electron to form an ion. Electronegativity, it is not forming an ion, it is simply sharing electrons within a bond. So, just like electron affinity, the trend on the periodic table increases from left to right across the row, so going this way, and then from the bottom to the top of a column it also increases, essentially following electron affinity trends, which tells you that the upper right of the periodic table has the highest electronegativity, the lower right has the lowest, is the idea of the, if you think of your periodic table. And here we actually have the examples. So you'll find that cesium has the lowest electronegativity. Fluorine definitely has the highest. In fact, fluorine is the most electronegative element of all. You'll notice that the noble gases are missing, and that's because noble gases in general do not form compounds. So they cannot share electrons, and they cannot pull them closer to themselves by definition. So the four most electronegative atoms are in red here. They are fluorine, definitely number one, then oxygen, then nitrogen, and then chlorine not too far behind. So FONCL is usually the acronym we give this. This is a good idea to remember this, these four elements. Definitely remember that fluorine is the most electronegative of all the elements. In fact, fluorine actually is used to set up the scale at 4. So 4.0, no other element has a higher electronegativity than fluorine. So it was actually set up based on fluorine. Everybody else has a lower electronegativity. So we can measure now polarity by analyzing the bond between the two atoms. So we have this atom and we have this atom. And the bond between them could be said to be of how polar it is depends on a few things, and this measurement is called the dipole moment, is given this Greek letter mu, and the units are debye, actually named after a famous chemist or scientist, Mr. Debye. So what you see here is that if the charge is, the greater the charge on the two ions and the longer the distance between them, the higher the dipole moment. We're not going to really do too much with dipole moment. We're going to work with it more in a qualitative way. We're not going to do too many calculations with dipole moment. But just realize the higher the dipole moment, the more polar a molecule is, or a bond is in this case. And we can measure mathematically how polar a bond is, and this is done through dipole moment. So if you take a look, here are some dipole moments of different molecules, and you'll notice that the higher the dipole moment, here we have a high dipole moment, you get a high electronegativity. This is the electronegativity of the two. If you have a low dipole moment, you have correspondingly a low electronegativity. And again, using color coding, HF shows a very high dipole moment and high electronegativity because most of the electron density is actually situated on the fluorine and not much on the hydrogen. Now, this essentially is what we use. We use electronegativity to decide if a bond is covalent or ionic. If the electronegativity difference between the two atoms is small, insignificant, or close to zero, then it'll be covalent, but it'll be nonpolar covalent. Think of nonpolar covalent as the molecules themselves will not be sticky. When we say sticky, we mean the attractions between the molecules will be very weak, and that's because a nonpolar magnet, rather a polar bond is something of like a magnet, because you have a positive end, you have a negative end, and the two are attracted to one another. So if the electronegativity difference is in the intermediate range, you'll still get covalent compounds, but they will be polar. So think of these as mini magnets. They'll be attracted to one another. If it's a large difference, then we'll call them ionic. In fact, when the electronegativity difference is sufficiently large, one of the elements essentially just gives away the electron completely to the other element. They don't even share electrons, they just transfer electrons. And that's the definition of ionic compounds. So there's really not a very sharp distinction between the three, but in general, this is kind of the case. In general, metal and nonmetals fall in the ionic range. All nonmetals in general fall here in the covalent range. So let's take a look at these. We can actually ask the question, which bond is more polar? So here we're actually just looking at the bond itself between the two elements. So you have BCl versus CCl. Let's actually consult your periodic table. So for the first one, we have BCl, boron and chlorine bond, versus carbon and chlorine. And technically we have to consider electronegativity differences. So recall that fluorine is the most electronegative element of them all, and we're essentially comparing carbon versus boron. Because carbon is closer to fluorine, carbon has a higher electronegativity. So carbon will actually pull electrons toward itself more than will boron. And because it pulls electrons closer to itself, carbon forms the more polar bond, and that's essentially the idea. So this one right here is the more polar bond. If we take a look at, let's see here, phosphorus and fluorine versus phosphorus and chlorine. Let's also take a look at the, so here we have phosphorus and fluorine and versus phosphorus and chlorine. So we know that phosphorus and fluorine, fluorine is more electronegative, so fluorine will pull electrons to itself more than the chlorine will, resulting in a more electronegative bond. So we got phosphorus and fluorine for our answer. Then finally, if we take a look at hydrogen, chlorine, and chlorine, this is kind of a trick question because in both cases the sharing is equal. Anytime you have a bond between the two of the same elements, the sharing essentially of the electrons will be equal. So if you were to draw it, draw something where you see there's exactly the same amount of electron density here as here, because the electrons pull with equal force. So in this case, we could say neither is the answer. And that wraps up for us lesson 2 of chapter 8.